Osmotic pressure, in simple terms, refers to as the pressure that stops osmosis. And we'll take a look at what that actually means. So remember that osmosis is the diffusion of water from areas of low solute concentration to areas of high solute concentration. Now, on the left side, we can see that we have that higher concentration of solute, and on the right side, we have a lower concentration of solute. So the water is going to move towards the left through that semi-permeable membrane, and the water level is going to increase on that left side over here, just how we see on this diagram of the final state. So the water is moving towards the area of high concentration to balance out that concentration on both sides. So in the beginning, when we have equal amounts of water on each side, the pressure is actually equal on each side. But as the water moves, as it moves and the water level rises, the pressure is going to be greater on the side with more solute. So over here, the pressure is going to be bigger than the pressure on this side. So we went from pressure equilibrium because we had the same amount of water, but when the water level rised on one side, that side had a greater pressure. And there's actually a mistake over here. P1B is not going to be equal to P2B. We can actually see that P1B is going to be larger than P2B. Over here, P1A and P2A were actually equal to one another. Now, when the water is moving up through this side, on the left side of the tube, we have this pressure, we have a pressure vector pointing up. But when we have that pressure vector that is equal and opposite pointing down, this pressure vector is going to be pointing down when the equilibrium is reached. So we have the equal concentration on each side. We get that equal and opposite pressure vector pointing down. And that pressure vector pointing down is essentially what is going to stop our osmosis from going any further because we've reached that equilibrium. And we can actually calculate that pressure vector because that pressure vector is referred to as osmotic pressure. So osmotic pressure is the pressure that is exerted downwards when that equilibrium is achieved. Now, the pressure vector is actually known as this formula over here, and we're actually going to derive this formula to understand how we can use it and how we can remember it instead of just memorizing it. But to quickly recap, I want to make things clear that in the final state, the pressure is going to be greater on the side with more solute because it has more water, and that pressure vector points up as water moves to this side. Once equilibrium is achieved, that pressure vector is going to be equal and opposite and pointing down, and that is our osmotic pressure. Whereas in the initial state, the pressure was equal on both sides. Now, if we, as we derive the osmotic pressure equation, we can remember that whenever we talk about gases, we know that we use the formula PV equals nRT. Now, if we rearrange this equation, PV equals nRT, and we move the volume to this side, and we get N over V. Well, we know that N, it actually represents the moles of whatever we had, whereas V is actually the volume in liters. So moles over liters is actually molarity. So we can replace the N over V with molarity, capital M. So now we have P equals MRT. Now we're going to modify this equation a little bit to make it specific for osmotic pressure, and we're going to replace that P with pi. So pi equals I MRT. That I represents the Van Hoff factor. And we can remember the Van Hoff factor as representing the amount of stuff that we have in solution. For example, if we have the ionic compound NaCl and it dissociates in a solution into its ions of Na plus and Cl minus, we have two things. So if we have two things, that is our Van Hoff factor, and that is equal to our I. So once we've modified this equation, we just replace the P with pi. So this is the osmotic pressure equation, and we can utilize this equation to determine our osmotic pressure once that equilibrium is achieved of the concentrations on both sides. Now, to quickly go through this once again, the I represents the Van Hoff factor, M, remember, is the molarity because we had N over V. R is the ideal gas constant, and in this case, the ideal gas constant is going to be 0.082. It's not going to be the 8.3 value. And then we have the temperature, and that temperature is going to be in Kelvin.